I'm going to talk about using trigonometric identities to solve trigonometric equations. All right? I'll assume that you know the basics of solving trigonometric equations. For example, I'll assume that you know some basic techniques to solve trigonometric equations. If you don't, I would invite you to watch the necessary videos. All right, let's continue. So, ideally, we would like to convert every trigonometric equation to one with a single type of trig function. Okay? Let me repeat that. Ideally, we'd like to convert every single trigonometric equation to one with a single type of trig function. So that's what identities help you to do. We will use identities to find equivalent versions of equations with respect to a single type of trigonometric function. All right, let's do an example. Suppose you wanted to solve this trigonometric equation. Cosine squared theta plus the sine of theta equals 1. And let's find solutions with respect to values greater than or equal to 0 degrees and less than 360 degrees. Okay, so you hopefully know how to solve an equation that has just cosine or just sine in it. All right, this one unfortunately has both. But if you know the Pythagorean identity, in other words, if you know that the cosine squared of theta plus the sine squared of theta equals 1, then you can solve for the cosine squared of theta in terms of the sine squared of theta. All right. Can you see how that allows us to do a substitution that will create an equation in terms of just the sine of theta? So now let's replace the cosine squared of theta in the original equation with 1 minus the sine squared of theta. Okay, now we can solve that for the sine of theta. So let me subtract 1 from both sides. So what do I have? I have that the, and let me factor out the sine. So the sine of theta times 1 minus the sine of theta is equal to 0. So the sine of theta is equal to 0, or the sine of theta is equal to 1. So now we can rattle off all the angle measures with respect to sine values 0 and 1. So for 0, we have 0 degrees and 180 degrees. For 1, we have 90 degrees. Okay, and maybe you want to order them from smallest to biggest. So if we do that, we'll get 0 degrees, 90 degrees, and 180 degrees. Okay? So once again, we are using identities to convert equations into versions with a single type of trigonometric function. All right, let's do another example. What about 2 sine of gamma plus 1 equals the cosecant of gamma? And once again, let's solve for values greater than or equal to 0 degrees and less than 360 degrees. So for this one, I would suggest using the identity that turns the cosecant of gamma into an expression with respect to the sine of gamma. The cosecant of gamma is equal to 1 over the sine of gamma. All right? Now, let's multiply all the terms by the sine of gamma. So 2 sine squared gamma plus the sine of gamma equals 1. 2 times the sine squared of gamma plus the sine of gamma minus 1 equals 0. All right, so now we can factor that, I hope. Let's see, 2 sine of gamma, and then another sine of gamma right there, and then 1, let's make it plus 1 there and minus 1 there. Okay, so the sine of gamma is equal to 1/2, or the sine of gamma is equal to minus 1. And once again, now we can rattle off angle measures that have sine values of 1/2 and minus 1 with respect to our desired interval. So for 1/2, that would include 30 degrees, and 180 degrees minus 30 degrees, which is 150 degrees. And then for minus 1, we've got 270 degrees. And that's already sorted from smallest to greatest, so there you have it. Okay? Now, I would like you to solve an equation that initially has more than one type of trigonometric function. Would you please try to solve 2 sine theta equals 3 times the cotangent theta, and find values with respect to angle measures between 0, greater than or equal to 0, and less than 2 pi radians. All right, so pause the video and do that now, please, if you can. All right, so I'll go ahead and work this one out as well. First, let's replace the cotangent with cosine, the cotangent of theta with the cosine of theta over the sine of theta. All right, we still don't have a single type of trigonometric function, but let's keep going. Let me cross multiply. 2 times the sine squared of theta equals 3 cosine of theta. Now, let me use the Pythagorean identity to replace the sine squared of theta with 1 minus the cosine squared of theta. Now let me expand, let me distribute the 2. 2 minus 2 cosine squared theta equals 3 cosine of theta. So let me move all the terms to the right side. So I get 2 times the cosine squared of theta plus 3 times the cosine of theta minus 2 equals 0. And so now I can factor that, I hope. So let's see, 2 cosine theta there, cosine theta there, and now we have to get a minus 2. How about a plus 2 here? And let's put a minus 1 in the first binomial. All right, 2 cosine squared minus, yep, that checks out. All right, so the cosine of theta is equal to 1/2, or cosine of theta is equal to minus 2, but minus 2 is not in the range of the cosine function, so we'll discard that. So we have to find angle measures such that the cosine of theta is equal to 1/2. So that will include pi over 3 and 5 pi over 3. All right. Now, would you please do one more exercise, one that's slightly more difficult, just to make sure you got this down. All right, try to solve this trigonometric equation. And find solutions with respect to values greater than or equal to 0 radians and less than 2 pi radians, okay? So pause the video and do that now if you like. All right, so I'll go ahead and solve this. So we've got 4 different types of trigonometric equations. So we're going to have our work cut out for us. So let's first do this. Let's replace the 1 over secant squared theta with cosine squared theta. All right, and we'll keep the 3 cosine of theta. On the right side, let's replace the cotangent of theta with the cosine of theta over the sine of theta. And let's replace the tangent of theta with the sine of theta over the cosine of theta. Now we get some cancellation, which is always nice. The sines cancel, the cosines cancel. So we're left with 2 on the right side. Let me subtract 2 from both sides of the red equation. So I get 4 cosine squared theta plus 3 times the cosine of theta minus 2 equals 0. And I don't think that can be solved using factoring. So let me use the quadratic formula. Well, even if it could be solved using factoring, the quadratic formula will still give the right answer. So cosine of theta equals negative b plus or minus the square root of b squared minus 4 times ac all over 2 times a, where I'm calling the coefficient of the cosine squared term a, the coefficient of the cosine theta term b, and I'm calling the number, the minus 2 in this case, c. All right? So let's proceed to solve that, simplify that. So let's see. So the denominator is 8. The numerator minus 3 plus or minus what? 4 times 4 times minus 2. 16 times minus 2 is minus 32. Subtracting negative 32 is the same as adding 32. 32 plus 9 is 41, so plus or minus the square root of 41. Now, you can also confirm what I'm about to say using a calculator. Well, first of all, let me copy the 2 possibilities. Okay, so the square root of 41 is bigger than the square root of 36. The square root of 36 is 6, so minus 3 minus 6 is minus 9. So the first equation that I've arrived at will give is saying that the cosine is equal to a value that's not in its domain. Okay, that's what I was getting at. So we can throw that one out. And then we're left with the cosine of theta equal to minus 3 plus the square root of 41 over 8. That is not associated with any special value. So we're going to have to go with that theta is equal to the arc cosine of, and let me reverse the order of the terms in the numerator, the square root of 41 minus 3 over 8. Okay? Now, that is not the only solution with respect to the desired interval. We also have to include 2 pi minus that value. 2 pi minus the arc cosine of the square root of 41 minus 3 all over 8. Okay, we got it. I just barely squeezed it in there. So that is the complete solution set with respect to values greater than or equal to 0 radians and less than 2 pi radians.